Hi, this is ET370 in the second part of lecture one. What we're going to talk about in this part is the second half where we go into how the PN junction, the specific details of how a diode works. We'll do a little chemistry review. We'll talk about semiconductors and doping, and we'll look at the three, well, there's kind of two states, but we'll look at the three kind of scenarios for a diode when there's forward bias, reverse bias, and actually no voltage being applied to that diode. And so how does the diode work? Well, recall from the last lecture, we had the anode, the cathode, the minus signs here, all matching the current. And notice the arrow matches this arrow, the minus matches this minus. But really what's going on inside is you have a PN junction where the N is tied to that minus side. Again, this is the anode cathode, okay? These PN junction, this P part, this N part is made of doped silicon, which is a semiconductor, right? And the doping makes the semiconductor more conductive. So let's kind of do a small review on chemistry. So if you remember from your chemistry class, you have an atom, you got electrons floating around, you got the nucleus with the protons and neutrons. Right? And if you remember, these electrons exist at different energy levels. And the outermost electrons, the ones that are ready to move and conduct and kind of trade places with other atoms, these are the electrons in the valence. And the energy levels, well, how far is it ready to conduct or not, is related to this conductivity, okay? All right, so let's look at three different scenarios. Let's look at an insulator, a conductor, and a semiconductor. So we want to talk first about the conduction band. The conduction band is a band where if the electrons exist there, they can easily leave the atom. All right, so for an insulator, you got your conduction band, but you have a large band gap between the valence band, and the conduction band. So that means it's going to require a lot of energy to get that electron to be able to conduct, right? Now, will conduct given enough energy, but it's harder. So ceramics, plastics, rubbers, those type of materials we already know are good insulators, right? Okay, what about a conductor? Well, for the conductor, there's no band gap. The valence band and the conduction band sit right next to each other. And so the electron can easily leave the atom, doesn't take much energy to push anything out. It's just like, let's go. So metals, gold, copper, steel, right? All good conductors, right? Okay, well, what about a semiconductor? Well, a semiconductor is kind of like something in the middle, right? You have the valence band, the conduction band, your band gap, and it requires some energy to leave the band, but it's not like an insulator, but it's not perfectly like a conductor. That's why they call it semiconductor. And some common semiconductor materials are silicon and germanium. In fact, we are the location of where this recording is happening is in the Silicon Valley. Now, if you're watching from somewhere else, you might not be in the Silicon Valley, but at least this area, the Bay Area, is also known as the Silicon Valley for this reason, the semiconductor technology that has come from it. Okay. All right, so how do you make a semiconductor more conductive? Well, from this idea here, you can add energy, temperature, light, but if you add too much, it will burn, right? But you can see, yeah, adding energy is going to get you more conductive, right? What else? Well, we can apply this thing called doping, right? You've heard of doping before, and doping in the sports world enhances performance, right? Athletic performance. And so you can kind of do that same thing with semiconductors. You can add other atoms, mix it in, and they change the properties, and you get better conductive behavior, right? So let's look at a specific example where we're going to look at silicon and boron, right? So silicon has 4 valence electrons, 1, 2, 3, 4. And boron has 3 valence electrons, 1, 2, 3, okay? We'll also look at phosphorus, which has 5 valence electrons, 1, 2, 3, 4, 5. Okay, so we can take our silicon, which is our semiconductor, and we can dope it with either boron or phosphorus. All right, and let's see how this allows us to not only get more or less conductivity, but also get a selective conductivity so we can make our diode, right? Now, when these atoms get close, they will form very strong covalent bonds, right? Where they will share electrons, right? So if you get the silicon next to another silicon, these two go, hey, let's hang out together. And now these guys are stuck, right? Okay. So let's look at closely of what happens when I dope silicon with boron and I dope silicon with phosphorus. Let's see what we get. Okay, so let's look at the first one. Let's look at our p-type doped silicon. So what we're going to do is we're going to take silicon, we're going to sprinkle a little bit of boron in. Now, do I know how much? No, but these manufacturers, they have it dialed in with their engineering processes to figure out the perfect amount. But here's the main concept. Silicon, boron, remember this has 3, this is 4. And you can see that all these covalent bonds are made, right? Pairs, 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 pairs. But notice the boron is going to have a lack of an electron. And what we call that is a hole, right? And that means this has an extra positive, you could think of it as having an extra positive charge. Okay, now we're going to be a little careful of that, but you could think of it as a positive charge that can move, right? Okay, now let's look at the N-type. N standing for negative and P standing for positive, by the way, so according to that, corresponding with that positive charge. So here we had 5 valence electrons and 4. So let's look at what happens. If we sprinkle some phosphorus into the silicon matrix, what happens? Well, we got all these pairs of covalent bonds between the silicon. We even have pairs between the phosphorus, just like here with the boron. But here we have an extra electron, right? So we have an extra negative charge that's free to move around. It's kind of like these are in the conduction band in some sense, right? Now, note, both are neutrally charged. So there's not an overall excess of electrons relative to their protons, right? Okay, they're all balanced in that sense. So they're both neutral, right? I have this in caps here with the exclamation points, right? Right, so same number of electrons and protons. However, both are more conductive because this has a positive charge that can freely move and this has a negative charge that can freely move, okay? And so hopefully this sentence kind of is confirming what I just said. They have a P-type has an available positive charge carrier and N-type has an available negative charge carrier. Okay, good. All right, so let's look at our specific application of the diode. So what do we have? Remember, this is maybe the 5th time now. We have our diode symbol. We have ID going to the right. We have VD plus minus, minus matching here, arrow matching the symbol. Okay. Remember, in our basic first ET250 class, our arrows are defined as positive charge flow, right? And in this case, a diode only gets positive charge flow if you have non-zero positive voltage on the left anode side, right? And then our kind of check valve analogy allows current to go this way. Okay, let's look at the PN stuff and see if that confirms our intuition from before. Okay, so let's say we have our P and N type, we just sandwich it together. We still have the 2 terminals. Now this becomes our little diode. And remember, our diode kind of looks like this, right? Just a little simple cylinder with a band on it. Okay, remember, both are neutral. This has extra negative electron carriers. This has extra hole carriers, all right? So let's apply like a positive voltage here. Like we're taking a battery, putting the positive lead here, the negative lead here, okay? And let's see what happens. So we're in forward bias, yep. And when we have a positive charge, well, remember, positive and positive, they repel. So these guys, these holes get pushed to the right, or you could think of the electrons going to the left. Okay. Now over here, remember, like charges repel. So the negative and the extra negative charge carriers get pushed to the left. Okay. So what happens in the middle? Well, you have these holes here and these electrons. The electrons jump into the holes and they can keep moving because they're attracted to the positive charge. Okay, so let's think about, let me say it again. You have the negative here, the electrons in here get pushed to the left because negative doesn't like negative, so they get pushed to the left. They see the holes here, jump into the holes, and they keep getting pulled and attracted to the positive. So we get electron flow going from right to left. Okay, well, we know that electron flow and our definition of conventional current flow is opposite. So therefore, the electron flow going to the left is same as positive charge flow going to the right. And hopefully this is consistent with our intuition, right? Positive forward bias here, we get conventional current flow going to the right. Good. Okay. Let's look at what happens when we apply a reverse bias. Okay. So reverse bias is we put the positive side on this right side here. Okay. And let's see what happens. So we got our positive side here. We got the negative side here. So we reverse the polarity of the battery. And all the little holes, sorry, not the holes, the negative charge carriers here are attracted to the positive. Okay. On the left side, all the holes are attracted to the negative. Well, what does that mean in the middle here? Well, in the middle, can you imagine if all on the N type here, all these negative charge carriers went to the right, what's going to happen? Well, you're going to have some phosphorus in this area here that I've defined without any electrons. In that case, this is actually positively charged because now you have an imbalance of your electrons and protons. You're going to have more protons than electrons. So you actually have a positive charge. And over here, what's going to happen? If the holes actually move to the left, that means that these are getting filled with electrons in here. If they're getting filled with electrons, well, what does that mean? Overall, this little window of p-type material is going to be negatively charged because, again, there's going to be an imbalance of electrons and protons. Okay, so if I apply positive here, negative here, electrons go here, but now I have a positive and negative. And so what happens? Current can't flow anymore because this balances out. And what you've essentially created is, let's say I have a battery here, some source, and this is my diode. Internally, it's creating its own little resistance voltage. And they balance, and you know what happens if you have the two pressures balancing, no current flows. I equals 0 in this case. Either way, it doesn't matter. I equals 0. Okay. All right. So this is basically stating what I just said. What we call this window here is the depletion region, right? And that depletion region voltage will balance the external voltage and no current flows. Okay. All right, good. The last one is, let's just look at what happens when you have no external voltage. Okay, so we have no external voltage. I don't have any battery or anything. Think of it this way. You have your negative charge carriers here happily just sitting there by themselves. They're not being pushed left or right. You got some holes here, right? The boron's happy. And then right down the middle, maybe just through some random vibration or whatever, some of the negative electrons fill the holes, right? And so what you have in the middle here is you have some phosphorus without an electron, and you have some boron here with an electron. You have a little bit of positive charge, a little bit of negative charge, right? So you have a very thin depletion region, okay? Okay, so it's just like, it's kind of, maybe you think of it like a middle school dance, right? You have pretty much, the boys on one side, the girls on one side, and maybe there's a few courageous ones in the middle that are dancing together, right? Okay, not that I've had any experience with that, being one of the boys sitting on the one side, not dancing with anyone. But anyways, aside. Okay, so this little thin depletion region here explains why you have that forward voltage, right? Remember this IV curve, this little forward voltage, because you need, if you actually want to get this driven, you need some forward voltage here to overcome that little thin depletion region. And so that is explained by this. Okay, I hope this lecture helps you understand the tip of the iceberg of how a PN junction works and how a diode works from the silicon and the semiconductor perspective. Okay, thank you very much, and see ya.